Welcome to the Cardiovascular lab. This is the last lab in ME70, and in it we deal with a real engineering example of how to utilize internal flow equations to model a real engineering system. So this is probably my favorite lab in ME70 because we're taking the equations we've seen in class and applying them directly to a real engineering system. So the problem at hand here is dealing with the problem of aneurysms in the cardiovascular system. So a typical spot for the aneurysm, first of all the question is, what is an aneurysm? An aneurysm is when the pressure inside your arteries builds up enough for the artery wall to actually weaken and balloon out. And an aneurysm can be very dangerous if they pop, and then the majority of the blood going through the aorta, for example, could be rerouted into the body cavity, and you have a very low chance of survival once an aneurysm bursts. So treating them early and rigorously and effectively is really important. So one of the most prevalent places for an aneurysm, and one of the most dangerous, is in the region of your cardiovascular system called the iliac bifurcation. This is where the blood coming in from your heart through your aorta splits into your two iliac arteries. So the region looks something like this, where your aorta sees the vast majority of the blood going to your body goes through your aorta, and it has a diameter of about 25 millimeters. So that's a large diameter. There's a lot of blood going through that region. There's a lot of stresses on the artery walls. And what makes it even more dangerous is the fact that your aorta is splitting, so there's going to be some turbulent region on the walls in this bifurcation region, and that turbulent region creates more time for the blood to interact with the artery wall. In particular, the cholesterol in your blood can build up on the wall of the artery, which creates plaque buildup, and that's dangerous because the artery wall stiffens here and the pressure builds up in the fluid next to it. So we want to deal with the problem of designing a device to treat an abdominal aortic aneurysm, which could occur in the iliac bifurcation. This is the iliac bifurcation. And in order to do this, to treat this problem, you would do one of two things. You could operate on the patient and actually go in there and drain the walls of the arteries so that the aneurysm subsides, or you could insert a stent graft manually to try to protect the walls and give them structural rigidity. But for an older patient, surgery might not be the best option, so you might want to do something that's less invasive. So you could use an endovascular procedure where we will insert a stent graft into the iliac bifurcation via the femoral artery in your leg. So the way that works is you take a small, thin tube of wire mesh with polyester fabric that is collapsed to a small diameter, and you stick it up through the leg, up into the iliac bifurcation. Then you can expand it so that the stent graft opens to provide structural support for your artery walls, and then do the same thing on the other iliac artery, so that we have this device here which can protect this region of the artery. This is called a stent graft, and these exist. There's a huge market for these in the biomedical world. In order to motivate our problem further, let's go look at some pictures or some illustrations of what an abdominal aortic aneurysm looks like, and some pictures of what stent graft looks like. So this is an illustration of an abdominal aortic aneurysm, and you can see they're performing some sort of invasive surgery where they're removing the whole region of interest, and they're probably going to install a modified iliac bifurcation of some sort. So these things are pretty dangerous. They require some treatment. So one of the treatment options would be a stent graft, as so. So this tube here is stuck through your femoral artery, up through the problem region, and then it's expanded, so it's a bistable device. It has two stable conditions, one of which would be in this closed form, the other form would be in the open form over here. And then you provide the other leg of the device by going through the other iliac artery. So as engineers, we are interested in designing a stent graft for a patient with an abdominal aortic aneurysm. Now, we don't have to necessarily be fluid mechanicians to do this. We could be structural engineers, we could be product designers, we could be anything, but we still need to understand the stresses that are going to be induced on this product in the heart, or in the cardiovascular system. So let's go further and look at the problem at hand. We'll go back to the whiteboard. And we will pretend as if we want to understand the flow through this region of your cardiovascular system. So what are the ways of doing this? Well, in lab, you've seen particle image velocimetry. That's a fine way of getting velocity field information from which you can gather a pressure field and therefore stresses on the walls of the arteries. Particle image velocimetry would work in a laboratory setting where you could build your own geometry and maybe provide a controlled environment where you see particles upstream and then visualize where they go. That might not be the best option for doing something that's more real world with different geometries. It could be a time-intensive, expensive experimentation to give a bunch of geometries. So another option could be to do a more computational approach. So we could use computational fluid dynamics to solve for the flow inside this region. So we can use CFD. Now CFD is remember, it's the solving of the general fluid equations of fluid motion, so the Navier-Stokes equations. In this case, we're going to have a three-dimensional problem. It's going to be unsteady because the heart is a pulsatile pump. The geometry might be changing in time as it elastically expands and contracts, and blood might not be the perfect Newtonian fluid. Blood is shear thinning, which means that as you apply a shear force quickly on the fluid, the viscosity decreases. So the rate of the viscosity is a function of the rate of shear. So it's a difficult problem, but it's still doable. And there's actually a lab on campus here which solves CFD. Using CFD, they solve for the flow rate in this region of the aorta. So in order to solve CFD, we still need to understand the boundary conditions on all surfaces of this region. We can use the no-slip condition maybe on these walls. We need to know what the boundary conditions are upstream and downstream. So the problem at hand that we have today is we want to understand what the inlet pressure will be at this boundary condition. And this might seem contrived. However, we could actually back this out by measuring a volumetric flow rate, a Q, at this region. And Q can be measured using MRI, phase contrast MRI, which gives you an experimental knowledge of what Q might be. And then knowing Q, we wish to measure P. Measuring P experimentally can be difficult because you might have to insert pressure taps into this patient, and that's obviously not the most viable approach. This is one boundary condition, so this is what we're going to be trying to solve for today, knowing this. Of course, there are two more boundary conditions here, but we're going to choose to not solve for them. We could do the same. We could use the same approach that we're going to use to solve for P here to solve for these guys, but we're going to neglect that for this lab just because our experimental setup doesn't provide data for these two regions. So with that, let's try to understand how to model the flow from this point downward in your cardiovascular system in order to replicate the physiological effects of having a branching network of arteries and capillaries and whatnot, such that the flow here is effectively the same as if you had the exact body there. So to do this, we need to look at the biological system, the whole cardiovascular system as a whole. So we could draw a diagram, biological diagram of every single blood vessel in your system and then understand the flow through each one. And that's challenging for a number of reasons. So we would rather do some sort of an engineering abstraction where we can group blood vessels together into pipe elements that we can then model easily. So on the computer screen, we have a comparison of different ways of looking at the whole cardiovascular system. On the left, you'll see
a biological approach where you would draw out the different networking effects, the networking pipes and the branching pipes, and you could go into more depth and look at every single pipe and try to understand the flow through each one. We're going to take that one step more abstract and look at an engineering perspective of this problem. So this would be an engineering abstraction of the flow through the cardiovascular system, where we've lumped together different parts of the system into different pipes. So we have arteries, we have pulmonary veins, we have bronchial arteries, etc. And the light blue lines are the lines coming out of the heart that have been oxygenated, and the dark blue is what's going back to the heart to get pumped through the pulmonary system to get oxygen. And this is great. However, it too is fairly complex for our needs. And remember that the problem at hand here is to understand the flow directly out of the heart. So the aorta comes directly out of the left ventricle, and we wish to understand the pressure basically coming directly out of the heart into the iliac bifurcation, which is very far upstream in the whole systemic cardiovascular system. So we want to group everything downstream of this point into a few parameters that we can understand. So let's take this diagram and simplify it even further. So to begin with, we'll draw the heart, and it will have some regions: the left ventricle, right ventricle, the atriums, and we know the purpose of the heart is to pump blood through the rest of the body to feed tissue, so we can draw a massively parallel bed of capillaries and tissue. And notice how it's one element here, but it will in fact be a massively parallel group of blood vessels. And to connect from the left ventricle to the capillaries, we pass through the major arteries. So we can lump all the major arteries together in one pipe here. And as we said, the diameter of these arteries, on the order of 25 millimeters. And the pressure we're looking for is this pressure right here, so I will label that P. And as you go further through the major arteries, we can extend even more to the minor arteries, which will be further parallel, so the diameter continues to go down, but the number of pipes goes up, until eventually we pass through these elements called arterioles. Now, arterioles are the flow metering device. These are the restrictions between your arteries and your capillaries that allow for certain flow rate to occur in your blood vessels. So if you're exercising or if you have inflammation, you need extra blood flow to that region. So what the arteriole does is it constricts or expands the diameter of that blood vessel to allow for extra blood flow. And why is this useful? Well, if we look at the pressure drop between the outside of your heart, which is basically fixed based on your heart, the power of your heart, and where the blood is going to, which is fixed based on the fact that it's going to some atmospheric pressure eventually. The only way to affect flow rate is to change the resistance of this pipe. And how do you change the resistance? Well, we saw in the pre-lab and in class that the pressure drop through a pipe is equal to the flow rate times some flow resistance R, where R, for a straight pipe, this requires fully developed laminar flow, by the way. R for a pipe, we know, is 8 mu times the length of the pipe over pi times d to the fourth, or r to the fourth, actually. So if you change the diameter or the radius of your arteriole by just a small amount, the flow resistance changes by quite a bit because of the r to the fourth dependence. So without this r to the fourth dependence, the body might be designed in a different way. So this is pretty important in how the body meters blood flow. Okay, so we've got the arterioles, and then we're going to continue to branch further to the capillaries, and the diameter of these capillaries can be as small as 5 microns. So D is on the order of 0.005, wait, 1, 2, 3, yes, millimeters. This is millimeters.
Now, why might we want to have small diameters on these capillaries? Well, for one thing, we want to increase the surface area of absorption. The purpose of these capillaries is to, of course, provide nutrients to the body, so you want to have maximum surface area. You also want the speed of the flow through these capillaries to be slower than they would be upstream, because you want to have time for absorption. So remember, Q is V times A, and if A goes way up, because there's more surface area involved with the capillaries, then V must go down for a given flow rate. So that's the logic behind that. Just do remember that this is going to be a networking effect. So there's going to be, as you go further and further downstream, there's more and more parallel pipes. So the surface area is increasing. Now from the capillaries back up, so I'll label this as the capillaries. And of course this is a very simplistic approach, but it's all that we need to understand the effect of having a flow below our iliac bifurcation. So this is the region where we're looking at, pretty much right downstream from the heart. Now from there we have the venous system, which takes us back to the heart. And then the heart pumps through the pulmonary cardiovascular system. This is lungs, which pump back into the heart. And we know that the pressure at the end of your venous system is atmospheric pressure. Otherwise, if you pricked yourself, you would have spurting blood coming on your cuts. And you know that that's not the case. This is clever because the heart doesn't want to provide any excess pressure, so it's efficient in this regard. And then likewise, the same is true for the pulmonary system. So the pressure coming out of the pulmonary region, pulmonary artery, or pulmonary vein, I believe, pulmonary artery, pulmonary vein, is also PATM. And if we're only worried about the flow in this region, we actually can neglect the entire pulmonary system as a whole, because the effect of it is not felt, because the atmospheric pressure is the same coming in from both the pulmonary system and the systemic system. This is known as the systemic system. Now, just for some reference here, we see this valve here. It's called the aortic valve, and this is the mitral valve. And we're going to model these valves experimentally, which we'll talk about in a second. They're very efficient because they don't require a large pressure difference across them to cause them to open. But at the same time, they don't over open if there's too much pressure across them. So you want them to stay closed, but have a small pressure differential to cause them to open. So they're very clever valves. Okay, so this is the biological simplification of the cardiovascular system, and we want to go one step further to model this in terms of an engineering system. And we've talked about the way that we can model delta P versus a flow rate. So let's do this using this circuit analogy. So we've seen this as sort of like an Ohm's law analog, where pressure is voltage and Q is current, so delta P equals QR. So we'll formalize that for a second here. We have the electrical world and then the fluidic world. And the reason we're doing this analogy is because there's a lot of literature and math and understanding that already exists behind the electrical, the equations that relate electrical systems. So we want to use those. So in electricity we have a delta V equals I times R. And in fluids we have a delta P equals Q times R, excuse me. So we're going to try to model this in terms of a bunch of resistors, and we'll see if that's going to be enough to get the effect that we want. So we're going to be using what's called the Windkessel lumped parameter model. In particular, we're going to be using a 3-element Windkessel model. So we're going to choose 3 circuit elements to model the effect of everything downstream of this point. And this isn't, there's literature on this. This is not something that you should have intuition on right away, but this is a model that exists in literature we're going to use. So the way it works is we'll have a voltage source or a pressure source, which is coming out from our heart, call that a pressure P. And we're going to model all the major arteries as one flow resistance. We call it R1. This is due to the major arteries. And then we'll model the minor arteries, arterioles, and capillaries, sort of everything down below the major arteries, as a second resistor, and we'll call that R2. And after that region, we're in the venous system where the pressure is P-atmospheric, so we need a potential difference to cause a flow to occur through this region. So that potential difference requires a lower pressure, which we can sometimes call electricity ground. So this will be our ground potential or our ground pressure, which we know is PATM. So this isn't complete. This, by the way, R2 we know is just, I'm going to say everything else, but it includes minor arteries, arterioles, and capillaries. Now if this were our model here, let's just think what would happen for a second. If I input a pulsatile signal, a pulsatile flow P upstream here, all the R's, R1, R2, all they will do will scale the result to have a pulsatile signal at the output. And what do we know about the flow through the capillaries? Well, we know it's a steady state flow because we want to have our nutrients delivered in a steady fashion. So there needs to be some other element in this circuit, some other mechanism to cause a steady state flow. So what does your body do to perform this filtering effect? What does it do? So what it does is it stores flow in the elastic expansion of the arteries, so that when during the low pressure stroke, this diastolic portion of your blood, of your heart pump, the elastic nature of your arteries will squeeze the volume of your blood through the rest of your system to like smooth out the pressure pulses. So it's the compliance of your arteries which allows for this smoothing effect, this dampening effect. And how do they model the compliance of your arteries? Well, for one thing, I sort of gave it away by telling you that it's a filtering effect, so you should be thinking in the realm of filters. And if you've seen a circuits class, you would know that a filter requires, one type of filter requires R's and C's, so we can model the compliance of our arteries by the flow capacitance. And the intuition behind this is that the storage of volume in the elastically stretched arteries is analogous to the storage of charge on the plates of the capacitor, which means we need to relate charge and volume, which we can do quite simply. So before we write our capacitor in here, let's look at what capacitance is. So in electricity, we know that the capacitance C for say, we have parallel plates, is going to be a change in the charge buildup. So if you apply a charge difference across parallel plates, you'll see a potential difference. And that's going to be equal to the capacitance of our capacitor. In order to write the analog in the fluidic world, let's understand what Q and V are. So Q, first I is the flow of charge, and so it's the flow of charge, and we know that in fluids the current analog is flow rate, and the flow rate is the flow of volume. In particular, it's going to be V water, because we're dealing with water in this lab. So that tells us that to get capacitance, I can say it's a delta V water, and we know that voltage is going to be analogous to pressure over a delta P. So we can take our elastic artery, we can pump a little bit of extra volume inside, and we can measure the change in pressure inside that region, and that would be the capacitance of our artery. We're not going to model the capacitive effect using elastic tube just because that's difficult. Instead, we're going to model the capacitive effect just using a box. So our capacitor, as we've seen in the pre-lab, consists of a region of water and a region of air. And there's going to be an inlet and an exit. And the accumulation of volume is analogous to the accumulation of charge on the capacitor. So when you accumulate volume of water, the air gets compressed, so the pressure in the air goes up. So the restoring force back on the free surface of the water goes up. So during a low pressure stroke of your heart, you have higher pressure inside your capacitor to move fluid through and dampen out the high pressure pulses. So with that, you could measure the actual capacitance value just by simply doing what we said, by injecting a certain volume of water and measuring the pressure difference. Unfortunately, our capacitor doesn't have the ability to measure pressure. There's no pressure tap in this region. So we need to use some analytical equations and some assumptions to relate this to what our capacitance will be. And in the pre-lab, you were asked to show that this is approximately equal to the volume of air in the capacitor over atmospheric pressure. And the logic behind this involves ideal gas law, and it's making some assumptions about the relative change of volume of air versus the total volume of air. And I will go through this at the end of the lab. I don't think it's worthwhile to talk about right now. But all we need to know is that we can measure C. So we know a value of C based on the volume of air in our bodies. So with that, we know what our capacitor is modeled as, and we know how its effect is seen. But where do we put it in our circuit? So we have two options. We can put it in series and in parallel. The intuition behind this is to look at how the effect of capacitance comes up in our biological system. So the effect of capacitance is felt in the arteries, where it's a parallel effect. At any point along this pathway, blood has two options. It can either be stored in the region that's of the expanded artery, or it can keep traveling down the pipe. So it's a parallel effect of having this elasticity, which means that we need to model it in a parallel nature. Even though the capacitor might be this expanding elastic tube, it is in series with the rest of the flow. The effect of capacitance is that it's in parallel. So our capacitor will be modeled in parallel down here, and it will have an output as ground, which we take due to the fact that we wish for our capacitor to have atmospheric pressure in it to begin with. And it will have a capacitance C. So now we have an abstraction for our biological system in circuit form, and we can use previously existing solutions of this circuit to solve for what the pressure is. And as you might know, this looks like an RC circuit, which could be denoted as an RC filter. So we're going to explore the filtering capacity of this circuit. Before we go any further quantitatively, let's take a qualitative approach at our experimental setup. Because we have in this lab a built circuit, fluidic circuit of this type, with an R1, an R2, and a C. So let's go take a look at our circuit and see what the effects of it are. Okay, so now let's take a look at the setup we have. So to begin with, don't get too worked up about all these pipes and tubes and wires. It's actually fairly straightforward. It's just jumbled up a little bit. So we can start by identifying different components in our system. So working left to right, we have our pump. This is going to be our heart. It has two valves, so we have 1, 2, and these are going to mimic the mitral valve and the aortic valve that we mentioned before. So this is going to be the aorta, or the major arteries, which comes out of the heart. This valve here is a ball and socket valve, where there's a ball that just rests into a cavity, and when there is a high pressure above the ball, it gets pushed in and seals the joint. When there's a negative pressure gradient above it, it gets pulled up and it allows for flow through it. And it requires a very minimal pressure drop across it for flow to occur. So this is the pump is meant for simulating heart. It has the correct shape, waveform of a flow rate, which we're going to look at in a second. And it's a positive displacement pump, which means there's a piston cylinder device in here, which pushes, causing the systolic part of the blood of the heart pumping, and then there's the retraction of the cylinder, which causes the diastolic portion. So systole is the pushing out, and diastole is the pulling in. That's why you get two ratings on your blood pressure. You get the systolic blood pressure, the high one, and the diastolic blood pressure, the low one. We're going to look at that in a second. There are a few knobs on the heart. We have a cubic centimeters per stroke knob. This represents the volume of the heart, so how big an animal we're going to be simulating. We have the pump rate. It's not worth looking at too much depth. Maybe it is. The pump rate is given in BPM, so we're looking at 60 or 50 BPMs right now, so a little less than 1 hertz.
And then the output phase ratio, percent systole over percent diastole. This is the amount of time spent during the systolic part and diastolic part respectively. All right, working our way further before we turn it on. I know it's tempting to turn it on, but it's nice to look at what we're going to be doing first. This is a flow sensor. We've actually talked about these flow sensors before in this lab, in the flow measurement lab. This is an ultrasonic transit time flow sensor. We have 2 transducers and a reflector, and the transducers send signals across the flow, and then depending on the time difference that those signals are received, we can back out what the velocity of the medium is going to be. And they're nice because we get instantaneous unsteady flow rate values. This is the pressure transducer, and we could have intuited that based on the fact that it kind of looks like it could be a capacitive pressure transducer. So there's a membrane in there which gets deflected via the static pressure of the water, and that deflection changes the capacitance value of the capacitor, which is then picked up in a circuit to back out what the pressure is. And it has an output of 1 to 6 volts, which corresponds to pressure of 0 to 10 psi gauge pressure, which we're going to write on the board in a second. But keep that in mind, that the values coming off of these sensors will be in volts, as any sensor does, maybe volts or current. And we want to know what the physical quantity is, Q and P. So we need to have a calibration or a transfer function that relates voltage and pressure, and then voltage and flow rate. Okay, working our way further, we have a resistance due to major arteries. This is R1 in our setup. It's a bundle of tubes which you modeled in your pre-lab. So you found analytically the resistance due to these tubes, and I believe the value you should have gotten was 7 millimeters of mercury per liter per minute. And note that was using blood for your working fluid, so mu blood instead of mu water. So if we want to use the current experimental setup, which includes water instead of blood, we need to divide by the ratio of mu blood to mu water, which is 4.6. So you should get about 1.3 millimeters of mercury per liter per minute for this R1, analytically. Working our way further, we see the box. This is clearly going to be our capacitor. It even says capacitance due to arterial compliance. And it has a few things on it which are worth pointing out. This is a pressure tap which is not hooked up, so we can't use it. This is a valve which we're going to use to change the height of the free surface, to change the amount of air in our capacitor, and hence change the capacitance value. And we're going to measure the capacitance value based on the volume of the air inside of it. So this is a 10 centimeter by 10 centimeter by 10 centimeter box, which means that if we read, right now it's at 84 millimeters on this scale, it's giving us 0.84 liters of air in this box. And there's a diffuser in there, so we got to keep track of the fact that that's going to be a diffuser, and it's going to have some turbulent exit region. Further, we have R2, resistance due to minor arteries, arterioles, and capillaries. You calculated the R2 value to be 107 millimeters of mercury per liter per minute, which, if you include the viscosity conversion, it should get you about 23.5, I believe, millimeters of mercury per liter per minute when we're using water. So we have an analytical calculated value of our R1 plus R2. And then we have another flow sensor. This will be our Q that's downstream. Another ultrasonic flow sensor. So now we can keep going further and follow our venous system back into the atmospheric exposed venous system. And then the pulsatile pump, if you look back at this tube here, which is wound all the way back up, it's drawing in water from the venous system at about p atm. So that's the macroscopic, the holistic view of our system. Let's turn it on and sort of see what happens here. There's some water, or some air introduced in the system. We'll let it even out and get rid of all this air. Sometimes it requires some TLC to do that. Getting there. If you look closely, you can see bubbles that sort of move and then stop and then move and then stop. there's some air in our flow sensor. Now whenever there's air in the flow sensor, we're not going to get a good reading for the flow rate, so we got to make sure it's just smooth, as laminar as can be. Okay, that's fairly good. So a few things to notice. First, we clearly have pulsatile flow in the inlet. This tube is even moving. And then if you follow the bubbles, you'll see that they literally go and stop, and then go and then stop. There's even some retrograde motion where the bubbles move and then come backward a little bit. Then if you follow the flow further downstream, the flow rate coming through the end of our circuit, if you look at the output, it's fairly steady. It's much more steady than the input flow. So it's modeling the compliance of the arteries via a capacitor, which is filtering the pulsatile signal coming out. And then this is also validated by looking at the sensors. So we haven't turned our sensors on. If you follow the cords coming back from this sensor here, we're going to call Q1. This is going to be flow rate coming through R1. And this is hooked up to this big box, which we can turn on. And we notice that the dial, just qualitatively, is very pulsatile. And then this same channel is hooked up to an oscilloscope. If you follow this wire back around here, it's hooked up to the scope, which we can turn on. And notice that this will correspond to channel 1. So Q1 will correspond to channel 1 on the scope, and this is important for you to look at because you're going to be trying to relate channels to flows and pressures in a second here. So Q1 is channel 1. It's also the furthest left in the setup. And then Q3, if you work our way over here, you look at Q3, which is pretty steady. Whoops. So you should see that the needle here is fairly steady. There's still some oscillations, but it's pretty much stuck over at a constant rate than the Q1 is. And indeed, this is validated also from the oscilloscope. So follow this wire back to the oscilloscope, and this is looking at the third channel, Q3. So right now we're talking about Q1 and Q3, which is channel 1 and 3. And look at the trace on the scope. So it's a little bit zoomed in right now. I'm going to zoom. Well, it's fixed itself there. So whenever you look at a scope, you need to understand what the zero values are. If you look at channel 1, the zero value, there's an arrow corresponds to the zero of that channel, which is right at that level, which means that there are regions of the flow where Q1 is equal to 0. In fact, the Q1 is negative, where there's retrograde flow. Conversely, channel 3, which is the purple region, which looks noisy, but really it's just zoomed in really far. The 0 for Q3 is below the 0 of the screen. You see an arrow or a purple mark there, which signifies that the 0 is down there. So this is much more steady than Q1. And then you see the third trace, the blue one. This is channel 2. If you follow this circuit back down to its sensor, it is the pressure sensor. So Q1, P, and then Q3. And remember that in this whole experiment, we're trying to back out what P is going to be given a Q1. That's the purpose of today's lab. Of course, we're measuring P, but that's only going to be used to validate our model, our predicted values. Okay, so we could do some fun things with the oscilloscope now with measuring blood pressure. We could introduce some cursors to measure the pressure, the diastolic blood pressure of our patient. We could gather information about that pressure, convert from a voltage to a pressure in millimeters of mercury. And in order to do that, we need to have the transfer function that goes between voltage and pressure. And we've said that it's between 1 and 6 volts and 0 and 10 psi. So let's go to the board for a second and actually write out the transfer function for this sensor. This is an important concept to understand, is that sensors output voltage in this case. And we want a physical quantity. So we have voltage, we have pressure. And in fact, our sensor is outputting psi, gauge pressure. And our voltage ranges from 1 to 6 volts, and our pressure ranges from 0 to 10 psi. And we assume a linear sensor, which is usually the case, or it's ideally the case. And we can relate a given voltage. We'll call it Vp, which we're going to read off the scope. This is a voltage at the pressure sensor, and we wish to know the corresponding pressure P. P
equals Vp minus 1 over 6 minus 1, which is 5, times 10 psi. And since we're dealing with a cardiovascular system, we want our pressures to be in millimeters of mercury because that's the standard unit for some reason. So times the conversion from psi to millimeters of mercury. We'll use 1 atmosphere. There's 760 millimeters of mercury in 1 atmosphere, and there's also 14.7 psi in 1 atmosphere. This is the conversion from voltage to pressure. Okay? Keep that in mind. Now, the same transfer function, or an equivalent transfer function, needs to be written for the flow sensors. So that is easier because the flow sensors don't have an offset at 1 volt. So Q1 is equal to 2.77 liters per minute per volt times our VQ1. If this is the value of on the oscilloscope, it corresponds to the Q1 sensor. And then Q3 equals 3.1 liters per minute per volt times VQ3. And of course, these are going to need maybe some remeasuring every once in a while. To measure these, it's super simple. We simply fill up a container of known volume and measure the time it takes for that to happen. So we get a Q, and during that process we measure a V, and that gives us the correlation between flow rate and voltage. We do this for each sensor separately. Okay, let's go back to the experimental setup and just sort of play qualitatively with what happens when we change our capacitance value, and start thinking about what might happen if you change the compliance in your arteries. So if you stiffen your arteries. And in fact, this is a physical phenomenon. Your arteries contain a material called elastin, which is the primary mechanism for elasticity in your arteries. And elastin has a half-life of about 70 years. So no matter how you live your life, your arteries will stiffen and your capacitance will decrease. And what happens when that occurs? This is also, of course, accelerated by arteriosclerosis, smoking, plaque buildup on your artery walls, etc. Now let's go look what happens qualitatively when capacitance decreases. Okay, so we'll turn the system back on. Make sure all the bubbles are out. It's not bad. Our oscilloscope is wacky here, so I'm gonna, oh, it fixed itself. I'm going to turn my cursors off just for kicks. Type off. There we go. And remember, just so we're explicit here, Q1 is yellow, P is blue, and Q3 is purple. Now, to decrease capacitance, I know that the expression for capacitance is the volume of air over PATM. I'm going to decrease the volume of air by opening up the valve. I don't want to go too far because the box is sealed, and if I overpressurize the air in the box, then the box can leak. And right away, the Q3 value becomes obviously more pulsatile. So it's the amplitude of its oscillations go up. And this is seen qualitatively if you look at the output into the venous system from the end of R2. It's much more pulsatile, and indeed this guy is more pulsatile also. So we just modeled the effect of aging and plaque buildup on the artery walls. So we could play more with this by measuring different blood pressures when we change the heart rate. So if I increase the BPMs up to, let's say, 65, everything sort of shifts around a little bit. And we can measure heart rate at blood pressure at different heart rates. We can change the volume of the heart that the heart displaces. I'm not going to do that because it's not extremely interesting. We can change the phase of the heart, the systolic versus diastolic phase ratio. But I think we understand sort of the general layout of our circuit here. We have 2 R's and a C. I'm going to turn this back down to 50 BPM. So now remind ourselves that we're going to try to use this circuit in order to understand
P. We're going to back out what P is using Q1, which is the yellow trace. And we're going to save Q1 data on this USB stick. And we're going to go into MATLAB and we're going to use the solution to the circuit. And then we're going to try to back out what P is. So let's go back to the whiteboard for a second to do some more quantitative analysis. Okay, so I mentioned earlier that we're using the circuit analogy to take advantage of pre-existing equations and knowledge about solving the circuit equation, solving the circuits. And we're going to go a little bit into that right now. So what we've done is basically built a filter. We built an RC filter. And in particular, this is a low-pass filter because we take some sort of a Q1 as a function of time that is pulsatile and it has some periodic nature to it. And we passed it through some sort of a device. In this case, it's a fluidic circuit that is a low-pass filter. And we get out Q3, which is also time dependent, but it's much more steady state. Now the filtering mechanism we haven't talked about how to quantify how much it's filtering. And the way to do this is to look at the different frequencies in the input signal, and the filter actually takes some of those frequencies, lets them pass through, in particular the low frequencies, and then cuts off all the high frequencies. If we model this as an ideal filter, there will be a cutoff frequency, omega c, which we define as the cutoff frequency, above which our filter does not allow signals, and below which the circuit does allow signals. Which requires us to understand how our input can be composed of different frequencies. So this input signal here can be seen as a superposition of a bunch of sines and cosines. This is called Fourier analysis, and it's a super important engineering concept. It's also super cool. So we can decompose our Q1, this is Q1, as some mean value plus an infinite sum, if I had equal sign here, of a bunch of sines at certain frequencies and cosines at certain frequencies. And we can solve for the coefficients in these frequencies with math, and MATLAB can do this super quickly. It's called the Fourier transform. And then we can understand how much of our signal has certain frequencies involved. So this signal is composed of certain omega i's, and any omega i's that are bigger than omega c get locked off, and we're left with our output signal. Now, of course, for engineering, we can't use an infinite sum here, so we'll make this just a big number and make this approximate. So we won't be able to reconstruct this signal exactly with sines and cosines, but it will be very close. We'll see. Okay, now how do we know what the cutoff frequency is for our circuit? Now this is sort of not the purview of this class. This is one of the reasons why we're using electricity as our analogy, because we can cite other work and other circuits. But we know for a circuit like this, omega c is equal to 1 over 2 pi times R2 times c. So, if I know R2 and c, I will know omega c, the cutoff frequency, and then I can understand how much of my input signal is being locked up. So what we're going to do next is that we're going to use the input Q1, decompose it into a bunch of sines and cosines with different frequencies, and use these as input signals to our ODE, which is the solution to our circuit equation. So what we can do is we can write Kirchhoff's current and voltage laws, whatever you want to do at each node, write this constitutive equation for each circuit element for the R's and C, and we can solve for what the pressure will be, or the potential will be in the circuit at any point. We want to solve for P here. This is where our physical problem exists. So we're going to utilize the solution to the circuit, which is an ODE, and the ODE is already inside MATLAB for us, so we're not going to derive that here. And then we're going to pass in periodic signals, sines and cosines with different frequencies and amplitudes into that ODE and get out what our pressure will be. Okay?
And keep in mind what will happen if we change R2 and C. If we change C, let's say we decrease capacitance like we did just a second ago, omega C goes up, so our cutoff frequency goes up, and we're a low pass filter, so we're allowing more of the input signal through. So this Q3 will end up being more pulsatile, have more amplitude swing. Okay, now in order to do this analysis, of course, we're going to need quantitative understanding of what R2 and C are. In the pre-lab, you said that you measured R1 as, I believe it was 1.3 millimeters of mercury per liter per minute, where we've already accounted for the viscosity change between blood and water. And then R2 is 23.5, I believe, 23.5. It's 170 divided by 4.6 millimeters of mercury per liter per minute. Now these are just the resistor banks, the banks of tubes. But in reality, we have other resistances. We have head losses due to the pipe, due to the exits and entrances, due to the other head losses. And so the effective R1 plus R2, the total resistance of our circuit, will be greater than this. And in order to get a value of R2 that's physical, I need to measure it. So we're going to measure the value of R2 and R1. But I can't really separate my circuit in two because the capacitor sits here and I can't undo it. So the question I have for you is, how do we measure R1 and R2 using the equipment that we have in the lab? So if you just take the equation for pressure drop in a pipe and you measure a delta P and you measure a flow rate, that won't help you very much because this equation doesn't hold including the capacitor. This is you have to take into account the total impedance of this whole element, the R's and C's. But what we could do is we could try to get rid of the capacitor. So we could unplug the capacitor and then run it, but that's difficult because our capacitor our flow goes through the capacitor. But we could also try to negate the effect of the capacitor by inputting a steady state signal, because capacitance only comes into play when you have a time varying potential, voltage or pressure. So we'll send a steady state signal using a steady flow pump that supplies a constant flow rate and a constant pressure through our circuit. The capacitor effect will drop. And the R1 and R2 value we can measure by just measuring the delta P across the whole circuit, from up here down to PATM. Now this is important because the pressure sensor gives us a pressure, and it assumes that the zero pressure is PATM. We're going to assume that the output is also at PATM. If we stick the output of our tube under the bucket of water, then the output will be at a different pressure than PATM. It will be at a rho GH. So we have to make sure that the output is at indeed atmospheric pressure. Okay, so now if we measure these R1 plus R2 values, we still need to have R2. And for this, I'm going to say that the ratio of R1 and R2 is as we predicted in the pre-lab. So I'm just going to say that R2 is going to be R1 plus R2 times the ratio of R2 to the total value that we calculated here. Okay? Also note that if this truly is laminar fully developed flow, then my resistance should be the same for no matter what the flow rate is. We'll see that that's not going to be true here, and that's just going to be due to the fact that we don't have true laminar flow everywhere. In fact, if we tweak up the flow rate to a high enough value, we're going to have a very turbulent flow, and the flow rate, and the resistance itself will be a function of flow rate. So we're going to get a very non-linear relationship between pressure drop and flow rate. Okay, so I said we're going to supply a steady state pressure and flow rate. We're going to do that using a steady state pump. And that pump itself is powered by a certain voltage. We're going to use a variable transformer to power the pump. And we're going to be using on that variable transformer a voltage that ranges from 70 to 100 volts. So I will supply a pressure of a voltage here, 70, 80, 90, and 100 volts. And I want, at the end of the day, I want different R1 plus R2 values. And in order to calculate R1 plus R2, I'll need a P and a Q. So I will measure my Q and P. But as we know, our sensors don't output P's and Q's, they output V's.
So I will measure from the oscilloscope a voltage is reading the pressure sensor and a voltage on the flow rate sensor. And it doesn't matter if I use Q1 or Q3 since it's steady state flow. The flow rate through these two resistors will be the same. So I will say arbitrarily we're going to do Q3. And I will fill in the table. And I will try to get different R1 plus R2 values at different flow rates, and then we will see how those resistances compare with different flow rates. So in order to use the steady state pump, I need to unhook my pulsatile pump, and I'll use this blue pump that's submerged under the water there, and that is my steady state pump. So I'm going to hook up that circuit and replace in exchange for my pulsatile pump, which requires undoing this thumb screw here. Being careful not to break the flow sensor Q1. There we go. Now to power the steady state pump, we have it hooked up to a variable transformer, which we've seen in other labs this quarter. This guy here. So right now it's at 0 volts, and if I tweak it up to about 70 volts, flow starts to occur slowly. And there are lots of air bubbles in this flow, so I'm going to try to get rid of those air bubbles by taking the flow rate up further and taking them all out. Alright, cool. So we notice that the capacitor has a constant volume of air in it, which means that the capacitance, well, at least the capacitor isn't being used. Alright, and I want to take pressure and flow rate measurements at different voltages. So I'm going to turn it all the way down to 70 volts first. I'll have someone hold it here because we don't want to introduce any extra resistance. If I kink the tube or if I dip it under the water, then my output pressure will not be at atmospheric pressure, or I will introduce some different flow resistance here. In fact, I'll just hook it right like that. And I want to measure my P and my Q3 in voltages, and I'll convert them into millimeters of mercury and liter per minute. And then I will use the equation for flow resistance, or the relationship between pressure and Q to get flow resistance. So on my oscilloscope, I will force trigger to collect a new screen of data. There we go. Looks like my pressure is off the screen, so I'll bring it up. And then I'll press the measure button to measure mean values. And I will get pressure by measuring channel 2, which looks like it is still being measured. We can cut this part, but, oh, there we go. Okay, ready? Okay, so we've measured channel 2. The voltage pressure is 1.39 volts, so I will convert that into millimeters of mercury using our transfer function for the pressure sensor. And then we'll do the same thing for channel 3, the purple. We have its 429 millivolts. This is zoomed in, so it looks pretty noisy, but we can zoom that out. Well, I won't do that, but we could zoom it out to make it look smoother. So that would be one set of data for my R1 plus R2. We'd have to solve for R1 plus R2. And then I will increase my flow rate up to 80 volts. I'll press force trigger to capture a new screen of data. And I'll do this process again at 70, 80, 90, 100 volts. And I'll notice as I increase the flow rate, the output gets obviously more and more, there's more and more flow coming out of the output. And the pump itself is nonlinear, so if I go between about 80 and 90 volts applied to the pump, it jumps to this fast flow rate here. That's just a function of the fact that the pump is nonlinear. But when we look at the resistance values of different flows, we'll notice something interesting, which is that it's not a constant. So let's jump ahead to the point where we've actually calculated R1 plus R2, and let's discuss the reasons they're not going to be a constant. Okay, so we've jumped ahead and calculated R1 plus R2 values at different flow rates. We've neglected writing up the actual measurements because it's not important. What is important is that we see changes in R1 plus R2 values. They're increasing. And of course, even the lowest value, which is at a very low flow rate, is still greater than the R1 plus R2 value that we calculated, which would be about 24.8 or something. So there's something that we're not taking into account using these R1 plus R2 values, and that would just be the head loss due to the flow through the pipe, the viscous losses in the pipe, and the minor and major head losses of the bends and the expansions and the contractions and whatnot. Now, why aren't these constant values? This should be constant if it's all laminar. Well, it's not laminar for one reason. But even if it is laminar in the vast majority of the pipes, even in this flow rate, there's still going to be exits and entrance regions where you can't simply use the delta P equals QR equation. Because when you have a expansion or contraction, you have induced vortices and eddies, and that causes a change in the viscous losses in the pipe. We took data for more than just these voltages. We have data from 60 to 115 volts. And what we've done is we've plotted the pressure versus flow rate at these different steady flow pump voltages, and we see an interesting result. So let's go to the computer and look for a second. At low flow rates, this is flow rate on the X versus pressure on the Y. At low flow rates, the curve is approximately linear that relates pressure and flow rate, and that's to be expected because P equals Q times R is a linear proportion. And then the pump has a nonlinear region in here where it's quickly ramping up to a high flow rate. And then in the high flow rate regime, we see some sort of exponential fit for how the pressure and flow rate are related. And this turns out to be empirically modeled or empirically validated, because we know empirically that for turbulent flow, delta P is proportional to Q squared. And this is because R itself will be a function of Q. So delta P will be equal to Q times some R, which itself is a function of Q, which is proportional to Q squared. And we're seeing that experiment here validated. Okay. So what we need to do next is to capture experimental data for Q1, like we said we were going to. So we're going to model let's say we could use phase contrast MRI in the body to get a Q1 value. And we're going to use that value as an input to our ODE that solves the circuit equation. And then we're going to try to back out what the pressure will be. Now, before I do that though, I need to know what my R's and C's are. And I've calculated R1 plus R2, but I don't have a given value. I don't have one value. And this is a difficult question because there is no one value that's correct. The flow rate we know is pulsatile, so there's no one Q that we can pull off our R1 plus R2 value from. So we could try to take a mean value and see what the resistance would be at that mean value. But even that isn't correct because it's not linear above or below, so we might have to take a weighted average of what the flow rate or what the resistance would be at a high flow rate versus a low flow rate. This is a difficult question. This sort of highlights some of the non-idealities of our model here. We can't strictly rely on a laminar flow model in this system because we don't have laminar flow. But it will get us a pretty good first approximation, and we'll see how we can modify our model to get it to be better. So I'm going to go take some measurements. So we're going to store data for Q1, and then we're going to take it to MATLAB and try to back out what P will be. All right, now it's time to take some data. So we have this USB stick in here. We've got the experiment running, and we have the oscilloscope set to have at least one period of data, preferably 2 or more periods, and the amplitudes are all pretty generous so that we have as much data as possible. When we press the save button here, we're going to be capturing all the data that's on one screen. So we want to have as much data as possible on one screen. And remember what I'm doing here, I'm going to use the yellow trace to back out what the blue trace will be. And I'll press save. And it takes a minute to save to the USB stick, and what it's going to do is it's going to save 3 Excel files. They're going to be named some gibberish, and then CH1, CH2, CH3 accordingly. our MATLAB script requires file names that are called ch1, ch2, ch3 without the gibberish. So what we're going to do is input this data by lopping off the initial gibberish characters, and then MATLAB will import the rest for us automatically. And so each channel will have two columns, a time channel and then a voltage channel, a time column and a voltage column. And then we can use the calibration, the transfer functions that we've talked about before to convert those voltages into flow rates and to pressure. Okay, so done saving. I'll simply take it out, turn the experiment off, and we'll go to the computer and import this. Okay, so we've got our data imported. It's labeled ch1, ch2, ch3 in our directory we're working out of. And there's one M file in this directory called Cardio-Master. So I will run that file, and that's going to import our data. And the first thing it's going to do is ask us some things. So it's asking for the calibration constant converting voltage to flow for Q1 in units of liter per minute per volt. And I told you what that was. We measured it experimentally. It's 2.77, and that's the default value. So I could have just pressed enter. And it's asking us the same thing for Q3, which is 3.1. I'm pressing enter. And these first two plots here are simply the Fourier transform of our data. So remember, we had to convert our time series data into a summation of sines and cosines, and we're just taking this is the actual data coming out of the oscilloscope, and this is our approximated data using the fast Fourier transform, which is a MATLAB function, and it agrees fairly nicely. This is just to validate the fact that we've done the Fourier transform correctly. And if we look at this plot here, these are the coefficients AI and BI of our cosines and sines. So the blue line is the BI coefficients of the cosine, and we see that there's a large coefficient at about a little bit less than 1 hertz. This is the frequency on the x-axis here. And then as you go to higher and higher frequencies, there's lower and lower amplitudes of those signals. In fact, if you look at the frequency spectrum plot, this is the lower plot here, which is amplitude on the y and then frequency on the x, the majority of our signal is happening at about 1 hertz, a little bit less than 1 hertz. And this is to be expected considering we were running the heart at 50 BPM, so we're expecting the majority, the biggest amplitude of our signal to be at less than 1 hertz. Great, so we understand the Fourier transform, we understand that we've taken our data and split it up into cosines and sines. We're back to our command line here. It's asking us for the total flow resistance R1 plus R2. Now this is a value that we have to guess at, because we said we didn't know what the effective resistance was. Now we measured values that range between 32 and 56.9 millimeters of mercury per liter per minute. I am going to take a first guess and guess that we have a resistance of 50 millimeters of mercury per liter per minute. And then it's asking for the volume of air in the capacitor because we need the C value. And this, we didn't go over how to measure it, or we didn't measure it in the video, but I measured it and we get about 0.5 liters. And this is the plot which gives us the measured, the blue is the measured pressure, which is what we took off the oscilloscope, and the red is the predicted pressure, which is what we tried to back out. Now first things first, it's fairly good considering all we've done was guess the value of R1 plus R2. What do we notice? We notice the period is correct, so that it's in phase with the appropriate response. We see that this region here where there's this notch, this is called the dichrotic notch, which happens after the closing of the aortic valve. There's a high pressure region when the flow is very slow, because we know from Bernoulli's that as the velocity goes down, P goes up. And indeed, we're modeling that in our modeled data with this little notch right there. But we do notice that the mean value of our pressure signal is higher than it should be. So where something is wrong with our R1, with our resistance and capacitances. So my question is, what do we change to tweak the mean value to match the experimental mean value? And the logic behind this is to think of a time average signal. Remember that delta P equals Q times R. The Q is our input. The Q is known in this problem, and the only way to get a lower pressure is to have a lower resistance, because Q is a constant. So I'm going to go back and try to tweak my R1 plus R2 value by decreasing it by a little bit to try to shift the mean value down. This is not important. And I'm going to run, instead of running the entire script, I'm going to run the ODE solutions because the data is already imported. And I guessed 50 before, I'll guess 45 now. And I'll keep the same value on the capacitor. So my mean value is better, it's still too high, so I'll try once again. This plot, by the way, is Q3, just for kicks. Alright, now let's try 40. That's getting pretty good. That's good enough for now. And what else do we notice? We notice that the amplitude of our pressure, the predicted pressure, is lower than the experimental amplitude. And this is also a good question to ask and a good thing to think about. So what can we change to affect the amplitude of our output signal? Remember, the amplitude is going to be a function of how much on our filter we're cutting off. So we have a low pass filter, and the cutoff frequency affects how much of the input signal is being lopped off. And if I have lopped off too much, it means my cutoff frequency is too low because I haven't been letting enough through my filter because it's a low pass filter. So to change my cutoff frequency to become higher, remember it's equal to 1 over 2 pi R2 times C, I can decrease C. So I can try to decrease C a little bit. I will get rid of that and then keep going. So I said my R was pretty good, I'll keep it at 40. And in the C, I'll try taking it down to 0.45 from 0.5 liters. Still too small, I need to increase it more. I'll go down to 0.35. That's getting pretty darn good. It looks like I still could move the whole plot, the mean value, down a little bit. But for all intents and purposes, we have modeled the pressure in this iliac bifurcation via modeling the rest of the cardiovascular system as resistances and capacitances fairly well. We have modeled the effect of the dicrotic notch. We've modeled the amplitude pretty well. We've modeled the period of loading pretty well. So now we have a device that simulates the effect of the systemic cardiovascular system that we can use to test our stent graft and to try to take measurements on the stresses developed in the stent graft and maybe fatigue life of the device. This is pretty powerful stuff. Now before we end, let's think about what we didn't model that we could have done to get a better result for this system. Well, we've done the fluidic to electrical analogy. We've used resistors and capacitors, but there's still one element, some circuit element that we haven't modeled. And a given pipe or a given wire, all wires have a resistance, a capacitance, and an inductance. And we haven't modeled the inductance. We haven't done any equivalent analog to inductance in the fluidic world. So what might be an intuition for what the inductance will be in the fluids world? Well, you can think for a bit, and you could write out the constitutive law for an inductor for a wire. And we have for an inductor, the change in voltage across the inductor is equal to the inductance times the change in current over time. And this becomes, in the fluidic world, a pressure difference is equal to the inductance times the QDT. And if you stare at this long enough and you look at it, you can realize that the inductance here is sort of like a mass in F equals ma. Delta P is sort of like a force. If you multiply times A, it is a force. So we can multiply both sides times A. And this becomes an F. And this is a dq/dt, so it's going to have a dv/dt term in it. It's going to be acceleration. And this L has a form of inertia. It represents the inertia of our fluid going through the pipe. So that's the intuition behind the inductance. Now to get an actual value for what L will be, we can just do a quick momentum balance on a pipe. So let's say we have some arbitrary pipe in our circuit, and it has some flow rate Q1 and some flow rate Q2. Mass balance tells us that Q1 has to equal Q2, and we will allow for a pressure difference to occur across this pipe. And if we apply momentum balance, the sum of the forces is delta P times the, let's say this is going to be some cross-sectional area of our pipe and it has some length L, lowercase l. F will be equal to the time rate of change in our control volume of the momentum inside the control volume. And then the flux terms, what are they going to be? Well, they have the same Q in and Q out in the same area and they're opposite signs, so the net flux will be 0. So this becomes a delta P times A equals rho comes out, dV is equal to L times A, and that comes out of the integral. So we have a L times A times rho times dV dt. And then to relate dV dt to dq dt, I simply say that dq dt is equal to A times dV dt, which means that we can say delta P is equal to rho L divided by A dq dt. So this becomes our flow inductance. And we could have modeled this in our system. We wouldn't have actually had to build anything extra in our fluidic circuit because the inductance is inherent. We can't get rid of it. It's the inertia of the fluid. But we could have included it in our modeled circuit, in our electrical circuit, as either a parallel or a series inductor, depending on how the how we wanted to have the model happen. And in fact, the Windkessel model does include flow inductance, but we have neglected it. So that would be one thing we could add to make this model predict the pressure better. We also keep in mind that the flow is not laminar during the whole flow regime, during the whole experiment, during the systolic phase of the heart pump. So we would have to think about a better way maybe of relating delta P with Q. And we couldn't, if we did a different way, if we had a quadratic equation for that, we wouldn't be able to use this circuit analogy. So this is where the analogy sort of reaches its limits in using, if we have any sort of turbulent flow, we can't be modeling that very accurately. So in summary, we have we've taken the entire cardiovascular system and we've broken it down into more of an engineering system where we've modeled certain elements in terms of resistors and capacitors. We've solved that circuit equation using previously existing techniques, and we've inputted into that equation some flow that we've taken using a flow sensor, and we've used that flow sensor to predict the pressure in a region that we care about, and we've compared that predicted pressure value with measurements that we took in our experimental setup.